Okay, thank you all for staying. I wonder, you may all be now keen to know what is neuromorphic vision, and I added here computation because everything the brain does from the retina to the prefrontal cortex is to compute. So if you really wanted to know what is neuromorphic vision, in a nutshell, this guy called Carl Vermeer in Caltech, who's the father of all computers we have today, at the end of his career, got interested in trying to replicate or come up with new kind of circuits that could mimic neurons for the very simple reasons that most of the energy you're burning today in your computer is around 40 to 50% of the clock. And so if you can come up with something new that can compute, well, you open a new field and he changed the game. So first thing he did was, in the early days, is to focus on hardware, and the first thing they did was to come up with what they called the silicon retina that continued these days up to my lab. And basically these days here, you could see it was frame-based, meaning we were generating images. So what happened since then is that this field expanded, mainly from the PhD students of this guy, of Carver. And today, I think, the real game that this neuromorphic acquisition and field is doing is trying to go beyond the work of Claude Shannon that you all know. So for those who don't know, he came up with a theory that says basically that if you want to know how a signal is increasing and evaluating in time, you have to fix a fixed period of time, and every time at a fixed period you come and you grab the value of the signal. So you see, this is very inefficient because here something changes fast, so you hope you get lots of samples, and here nothing changes, and though you're still acquiring useless information. So this was very acceptable and really widespread like cholera in the days because people were using radio signals. So you can afford to lose energy by wasting computation time, memory, and processing useless information, throwing them away. But in the real 21st century, where you're getting data from all over the place, generating images using this principle is very inefficient because instead of having one signal, every pixel along time is generating the same amount of data. And today, with 4 million pixels and your tablets and your smartphones and the cameras, all this energy spent to acquire this useless information is transmitted, stored, and then most of it thrown away to keep only the essential part, which is basically where was the change. So why are we doing this? And to really understand why we're doing this, we have to come back in around 1544, where people invented the mother of all cameras, which this is the work of Leonardo da Vinci. It's called the camera obscura. So it's a dark room, you have a hole here, and basically they found out that you can project a scene. And this is the invention of the camera. And over the years, it became a job. This painter here used it to move from castle to paint people. And then this box, this huge box, was reduced to a very small box you can take when you travel. So you would put a piece of paper here. And then, of course, the paper evolved to glass and currently pixels. And the other evolution was to replace this very inefficient hole by better optic, cheaper in plastic, etc. So as you see, it's just old wine, in old bottles that we sell you again in new bottles. But the whole story is here. And when people moved in 1877 to video, of course we could acquire an image, so we acquired many of them, and we found out that by projecting 25 images per second, you get an impression of motion. So again, based on an incremental momentum of history, we are acquiring more and more redundant information because you see mostly everything here is the same, and the main information that's changing is very little. So the question is, why are images so bad? Well, I think all of you watch tennis lately or any sport activity. So if you want to see this pitcher doing a fast motion, you have to increase the number of images you're acquiring. And if you do that, you will generate a lot of images and then lots of data that you have to transmit. And when you do that, you get this very small pixels, very small amount of pixels where the change is happening. However, all around here, the grass is not changing, the people are not moving that fast. You are still generating useless data. So what people do today is they try to find the right trade-off between how much computation or broadcast they can afford, and versus what is a reasonable thing we can send you so you can watch something. So this is called the problem, the unsolvable problem of undersampling and oversampling. You will always oversample and undersample, and whatever you do, wherever you put the slider, it's always a trade-off between your computation and how much money you have to process the data. So currently, the main lock we have in the modern era is what is called the data deluge, which is currently every year we produce, if we stack all the data produced by mankind in DVDs, we can pile them, and that will give you the distance between Earth and the Moon. And the amount of data is increasing much faster than what we can process. And keep in mind that most of that data is absolutely useless and redundant. So what is the brain doing? Well, the brain, in all its form, at least at the periphery of the brain, whether it's the retina, the cochlea, or the olfaction system, olfactory system, is doing a very different approach. It's basically asking itself, I don't want to go and acquire information every dot of time, every period, fixed period of time. I want to react when there is something reasonable that happens. And basically, it's sampling on the other axis. It's basically asking itself, is the change significant? And if so, I'm going to send it as fast as possible and process it as fast as possible so I can react. And this is what we humans do, and most of animals do that. So what happens is the same volume of data here becomes very sparse. And currently, when you apply these kind of things, you can process the amount of 1 million frames per second on something close to an iPhone, of course, depending on what you want to do. So the major paradigm shift here is information is sent when it happens. When nothing happens, nothing is sent, nothing is processed, nothing is broadcasted, nothing is stored. It's very sparse, and time becomes the most valuable information you need to compute with. So this is not something science fiction. This is what we do in the lab. It was a very long path to reach these kind of cameras. So we call it the asynchronous time-based image sensor. So this camera here is something you can't buy. Actually, you can buy today because we have a spin-off. But what happens is that every pixel is independent and is sensing light and looking for a change. And when a change happens and is detected, well, we start an integration, meaning every pixel has to acquire the same amount of photon. And so instead of sending you a value saying, here I acquired 246 gray levels, 40, and sending like huge amount of data, basically here what you say is, every pixel sees a change, says I started integrating to acquire the amount of photon you asked me, and I finished. And if you look at the timing here, it's proportional to the amount of light you have. So if there is a lot of light, a pixel sees a change, starts integrating, finishes integrating, but the time is very short. And if there is not enough light, well, that would take longer. And so by sending a unified way of expressing that change, by saying, I see a change, I send you another event telling you I have started integrating and I finished integrating, you're unifying the way you're signaling the changes and how much light is there. And everything is done in the time domain. So this camera is very precise. It works at the microsecond time precision. And we have gray levels going beyond 143 dB. Keep in mind your iPhone is doing 50 dB. So it's a huge number of gray levels. So the space here is very different. At time 0, everything is new. So you get every pixel sends you something new. And as cars start moving, I'll show you this video later, you get every dot here is precise to the microsecond, and it comes with a change and the gray level of that change. So here is T0. This is image at time 0, and every dot you see here is signaling a change, and it comes with its gray level. And look here, this is the amount of data generated by a conventional camera to image this at 30 images per second. While this is the amount of data generated here for the same scene at 1 million frames per second. So it's around 5% for 1 million times more efficient. And this is why our brain is not the size of this room, because as you will see, computing this kind of stuff becomes very simple and very efficient. And so this is out of the scope of my talk, but we have rewritten almost everything that people have done in the last, since the beginning of the field of computer vision. So stereo vision here, you see it's slowed down. Every dot here is a 3D point reconstructed by 2 cameras. You can do all sorts of things like tracking faces, and even going beyond, like streaming is different because this camera is already compressing the data. So you don't need 4G or 3G with a simple edge network. You can still stream events uncompressed and get them on another computer at a very, very low computational cost. And so this is introducing a paradigm shift in the way people are thinking of artificial vision. So there are 2 slides with maths. I'm going to tell you why I'm putting this here. So everything people do with images is really, from my point of view, quite ugly, because this says if you're looking for motion in pixel xy from an image at time t, you have to look for a small displacement, delta x, delta y, delta t. It means that gray level has moved somewhere. And you end up doing all this first-order derivation. And just to compute velocity, you have to invert huge matrix. So meaning if you want to compute motion with images today, you have to invert this matrix for every pixel, for every image, which nobody can do. So what people do today using GPUs and selling you more and more hardware is really to compensate for this acquisition of images that is very, very inefficient. So how does it look like when we use events? Well, the equations are always much, much simpler. It's almost first year of university, most of the times. And so you get an event, and what this equation says is that if you take an event and you take the timing around that event, well, by 2 simple operations, you can find the velocity. So it means that we've shown that this can be done with neurons too. It means that for every spike you get from this artificial retina, you can compute this little arrow that gives you the motion. And currently, this is done very, very fast at the power of an iPhone, where people really hardly can go beyond 30 or 60 hertz on a conventional computer. And so what is it saying about biology? Well, if our algorithms are true, and if we're saying things about biology, this computation should work on real spikes. So what we're doing currently is to record on MEAs, pass bars like this, get the activation, which are events to us, which are spikes, and computing the same exact algorithm on these spikes from the retina. And the result you get is that here are ganglion cells, and here are the receptive field of ganglion cells, and what you see in red is the direction of motion of this bar, and in dark is what we have computed. So it means that I cannot tell you that the retina is exactly doing this or the brain is doing this, but given the fact that we are working in the same mathematical space, there are a high probability that this is what's going on in the brain, because there are no other ways to compute it mathematically. And this is what we've been showing lately, that every time you take real recordings, you apply our algorithm, well, they work quite fast, they work real time, and they work on every event. So what is the motivation of our team? Is really bidirectional work. We go from recording, where we work a lot with Serge and other people from the brain. We have applications, which are retina prosthetic robotics, and we design hardware and mathematical. And everything is flowing sometimes from the maths toward neuroscience, and sometimes from neuroscience toward hardware and more mathematical stuff. And first work we've done a long time ago now was to take all this diversity of ganglion cell, and Button here gave us data from the rabbit of all different types of ganglion cell that we fitted, and we ran a model, and what we found out is that using this high temporal precision retina output from our silicon retina to a flickering light like this, we can find the barcode of every ganglion cell known, and it matched the data recorded on biological cells. So this is, of course, very far from adaptation mechanism existing in the retina. However, it shows that if you have simulation tools and if you have the right mathematical space as a biological retina, you can somehow approximate and create new methodologies. And so keep in mind there are no images as far as I know, in the brain, and there are no videos, and what you see here is the response of different cell types. So not only are they not talking and spiking at the same time, but they're not even responding at the same locations, because here you have an on beta and off beta, local edge detector, colored differently, and you see they are responding at different times in different locations. And all this is completely asynchronous. I'm just showing you images because I'm smashing events, because all our current technology can't display 1 million images per second. So this was the starting point of a very nice and very fruitful interaction with José and Serge and with Pixium. And basically our job there was to develop all the tools that you need to activate implants, and people don't tell you about this, but this is a nightmare to do it. 50% of the pain of doing prosthetics is to design these things, because they have to comply with the whole biology and also with lots of painful regulations. So all the system must hold a day, and what we have inserted in these type of cameras is that the architecture here has an event-based camera. It is operating in the very high temporal resolution domain around the millisecond. And so we helped designing the new Iris 2 goggles. We developed from scratch the Iris 3 goggles. So basically, Pixium is doing this epiretinal implant, and they also work on a different kind of, so here basically what you have is goggles. The camera is here, it's sending the events at high temporal resolution to this pocket PC. And this pocket PC runs a simulation of the retina, defines which signal to send back to the implants that are here, and basically comes back and sends to a little chip here which electrode should light up and when. And as Valentina says, if you want to talk to the retina, because it is precise to the millisecond, if you stimulate it at 30 hertz, you will just have a shadow of a stimulation. Whereas if you want to really talk to the brain, at least at the periphery, you have to match the millisecond. And matching the millisecond means you have to process 1,000 images per second and run a model that runs 1,000 frames per second in real time, which I don't believe can be done today currently on holding a whole day with a conventional camera. So this was really a technology unlocking that happened, and this is what allows currently Pixium to really be much better, I believe, than the rest. And so the second work we are doing, and this is still on progress, is to develop goggles for optogenetics, and also for this second generation implant that Daniel have been developed and that we also slightly improved, is to basically, these are passive systems. So here cells are transfected. Here you have small photodiodes connected to an electrode, and you have to shine light to generate power to make the cell fire or the electrode fire. So what people don't tell you is that you have to match, if you want to do it nicely, as Valentina said, the 1,000 frames per second. And at the same time, you have to send something close to the power of the sun 7 times at 12 in the desert. So the question is, why don't you use these kinds of technology that currently are available, like Oculus Rift, or this is the new Samsung VR? It's because the technology used here is very inefficient and produces the power of candles on a birthday cake. And if you increase the power, everything will melt down. So the challenge was to design something that complies with all the medical regulations while sending 7 times to 1 times the power of the sun, while being able to process 1,000 images per second, while being able to process them to simulate and stimulate the retina. So many people wondered, why on earth would you need to stimulate the retina with 1,000 frames per second? I mean, I am seated on my couch, I watch TV at 30 images per second, and this is far from being sufficient. Well, the question is, when you do that, it's because today you can't go beyond 30 images per second, and because most of the display is done because you're seated on your couch. However, these guys here, like Oculus Rift, who are trying to put these kind of technologies in your car and help you drive drones in the sky, know that even if you go to 100 images per second, after a few minutes, you're completely sick. Because your system is tuned, as Button said, wired to operate at 1,000 frames per second. And So what you can do while seated on your couch, you couldn't play tennis at 30 frames per second because all your prediction system would be dead. So to have a very good stimulation, you have to match these 1,000 images per second. And we have the tools. We managed to really put everything in these kind of goggles, which is the last generation that will also have eye tracking and will also compensate for lots of things. And so the question we wanted, and we've been working now for 3 years very painfully, and lots of people in my team really had a hard time, is how can we show that stimulating the retina at a millisecond is indeed adding something? So we started psychophysics, and what you see here is an expanded version of the goggles. And the idea was, how is speed discrimination when you stimulate the retina at 30 hertz versus 1 kilohertz? And so here we came up with a series of tests with Jean Laurenceau, and the goal is you fixate here and we pass you a bar and a second bar. One bar is at 30 hertz or 60 hertz and the other bar is at 1 kilohertz. No, actually, one trial is at 60 hertz and the other trial is 1 kilohertz, and there is a difference in speed between the two bars, and we ask you which bar was faster. And basically when you do that, you can see that basically the more you increase the speed of the bars, while having a relative velocity of 3%, people can really sense that little 3% difference between the two speeds at 1 kilohertz, while when you keep the 60 hertz, it doesn't improve much. And the things become even more impressive when you look at how much difference there is between the velocity in the Weber fraction here that says that basically when you are at 1 kilohertz, you can match the sensitivity of the 3% difference between the two velocity I'm showing you, while when I display information at 60 hertz is completely lost. You can't make the difference, and people make mistakes. So step one is your speed discrimination is better if I send you 1,000 images per second. 2, we did a bar counting. This bar counting is basically asking the question, if I increase the temporal resolution, am I also increasing the spatial resolution? So here you fixate and we pass you bars with different spacing, and you have to say how many bars you saw. And as you can see here at 60 hertz, the more the bar passes fast and the more the spacing between the bar is small, the more the error is almost going to 50% error. And the more you increase the spacing of the bar, and the more you manage to give some right answer when it's slow, and when it increases, like when you're driving a car or whatever, they tend to collapse. While when you match the kilohertz, things remain absolutely stable, and people are always able to discriminate and tell you how much bar they saw. And the last experiment we did is trying to recognize numbers. So the story here is you fixate and we pass you numbers that are completely masked with 888, and when you're in the middle, you unmask one and you don't know where it's going to be. Is it first position, second position, or third position? And you have to report which number you saw. Here you see the rate of recognition in red for 60 hertz that collapses up to 30%, right, correct answers if you go to 60 hertz. While when you match the kilohertz, people always manage to see even for very, very high speed. And this is what you do when you're driving, and this is what you do when you play things. Resolution does increase, spatial resolution does increase with temporal resolution. And here you have the confusion matrix. For every digit we pass from 0 to 9, well, almost we have 90% everywhere of recognition rate, whereas for 60 hertz it goes from 50, 30, 20, it's completely erratic. And we pushed it even further. We wanted to know what is happening in the brain when you show you something around 1 millisecond versus 60 hertz. So we have this very known stimulus where you have dots, and every 3 hertz you have a coherent motion that you can see. At some point they all go in the same direction. And so we tried to see the activation of the cortex here, especially the visual areas. And this is what you get when you try to find the 3 hertz frequency from a 60 hertz simulation. It's not very clear, and you don't really find the 3 hertz. While when you match the kilohertz, this is really very clear that we can find the 3 hertz tagged stimulus. And when you see the activation here, this is the response, the signal-to-noise ratio. And you see that basically stimulating for the same amount of light, the visual cortex, I mean the whole chain of the visual chain with 1 kilohertz gives you 3 times more activation of the visual cortex. And now we're going for more experiments to understand that. But it is clear that the system is tuned to work at 1,000 frames per second, so no surprise. So what is the next step? The next step is currently everything we do to stimulate, to go for implants, is to compute. And currently computers are very inefficient because most computers are spending a lot of energy just to moving data from your memory to the processor, which represents something like 80% of the energy. Just moving data from the memory to put them in the processor to do some computation. And so this guy here called the von Neumann is basically the inventor of modern computers. It says basically if you have to compute all this, you have to pass them through this bottleneck, and so it takes forever. So currently what people are doing is they're putting more processors to sell you more processors, and nobody knows why, but anyway. It's not that efficient, whereas the brain is making no difference between memory and computation. And this is a huge paradigm change, because if you can't stop moving data from memory to processor, we will be able to compute a lot of things that we can't compute at very low power. So we could simulate more neurons and hold more than a day just doing all this. And so this is what we've been developing last couple of years, and we came up with this nice framework called the STIC that is basically laying down the principle of a new computer that we hope to, well, we are building right now. And it's based on the idea of coding numbers in the interspike. And basically all the logic here that we are using is just delaying lines, speeding lines, and just trying to get always, when you get 2 spikes, you release 2 spikes. And so everything becomes compact. Data is close to computation. And this, to our knowledge, is the first non-von Neumann computer. So you can compute everything we need to simulate neurons. Like a very complicated Lorentz attractor uses only 500 neurons, very simple neurons. And so if you have 1 million, you can imagine how many we can compute. So finally, as a conclusion, I would say that this paradigm shift of changing the way we really acquire signals, very close to what the brain is doing, will allow us in the near future to do things that are impossible today. For example, there are people in the team that are working on decoding in real time all kinds of signals at very low power, which will allow them to be implantable. So we can target locked-in people who can paraplegic or tetraplegic. We can target detecting pattern in the brain all the time, switch on, heart failures, spike sorting online, implanted in the brain, costing very little. We are already working in these fields quite heavily in robotics, on autonomous driving. And there is also, these kind of techniques are also introducing a change in the way people are thinking of decision making. Because if you want to do this, at some point you will have to simulate more neurons that can make decisions. So all in all, see, a very little shift in the way we acquire signal opens new and wide perspective, and this is it. Thank you. This is part of the team. We tried to bribe them with food to bring them, but nobody showed up, so not everyone showed up.